These are the notes for AP Calculus on the topic of points of inflection and concavity. So similar to the first derivative, when the second derivative is 0 or undefined, these are significant points called the possible points of inflection. They don't have a cool name like critical points or critical numbers like the first derivative does, but that's what they really are. They're places where you could have points of inflection. And the second derivative tells you also that when it's positive greater than 0, the original function is concave up. So the second derivative is positive, concave up. Shaped like a cup. And when the second derivative is less than 0, negative, then the original function is concave down, second derivative negative, shaped like a front. So points of inflection are where a function changes from concave up to concave down, or from concave down to concave up, assuming the function is continuous there. So we only have one name for them, points of inflection or inflection points. Same thing. Unlike relative extrema, which can be relative minimums or relative maximums, depending on if the first derivative changes from positive to negative or negative to positive. And the second derivative, if it changes sign either way, they're points of inflection. All right, let's look at a few examples here. This first one says, state the x coordinates of any points of inflection and justify your answer. So first we're going to state the x coordinates of points of inflection, and then we're going to justify the answer. So, let's see here. Our first derivative, f prime of x, since we need the second, we need the original function, we need the first derivative first, would be 12x minus 4x cubed. And then we get to the second derivative, f double prime of x, would be 12 minus 12x squared. And then we set the second derivative equal to 0. In this case, there's no denominator, so it's going to be an undefined. You factor out the 12, you're left with 1 minus x squared. And you can keep that. If you want, you can take out a factor of a negative 1, but you don't have to. If you leave out, you can put factor in 1 minus x and 1 plus x, and it's a perfect squares factoring. And then you take the things that make it equal to 0, in this case 1 and negative 1, and you put those on the number line. These are our possible points of inflection. And then we can test negative 2, 1 minus negative 2 is going to be positive. 1 minus negative 2, plus negative 2 is negative. Positive times a negative is negative. Between negative 1 and 1, you could test 0. 1 minus 0 is positive. 1 plus 0 positive. Positive times a positive is positive. You could test 2. 1 minus 2 is negative. 1 plus 2 is positive. Negative times a positive is negative. So this shows us that f of x, the original function, when the second derivative is less than 0, negative, it's concave down. Second derivative positive, concave up, back to negative, concave down. And let's see, our possible points of inflection, negative 1, the graph does switch concavity. So this is a point of inflection. And at 1, the graph also switches concavity, this time from concave up to concave down. So in this case, both of our possible points of inflection actually are. So we can say f as points of inflection at x equals negative 1 and x equals 1. Since how we justify it is we refer to the second derivative, f double prime of x changes sign. You could say at x equals 1 and x equals -1, or you could say at these points. All right, let's go to the next example. This one a little different because it says consider that differential function with the given first derivative. So we're already starting with the first derivative. And again, we're asked to find the x coordinates of any inflection points. That's the first thing. And then the second thing says to state the intervals on which f is concave up and concave down. So we're not just to find the points of inflection this time, but we are stating the concavity intervals, which we didn't do last time. But since we already have that, we have to take it out at once. So f double prime of x. And notice here it's a little more complicated derivative. And x squared minus x cubed. So now that's going to be the product rule. So what we're going to do is 2x times the second one as it is, x squared minus 4 cubed, plus the first one as it is, x squared. And then we take the derivative of this. That's going to require the chain rule. So power on the outside, writing down with 3 times 3 squared minus 4 squared. It's power, but then almost like we can multiply by the derivative. Root of x squared minus 4 is 2x. Then to make this simpler, we reset this equal to 0. And there's no denominator, so we don't have to worry about where it's undefined. But what we want to look for is the way to simplify this to solve for 0, and that's by factoring. So this is all our first term, plus this is our second term. So what do we have as a GCF? Well, they both have 2x. So we can factor that out. And they both have x squared minus 4s, cubed and squared, so factored out the lower exponent, which is squared. Now let's see what we have left of each term. For the first term, it was x squared minus 4 cubed. Factored out 2 of them, so now just one of them left, x squared minus 4. Could say to the first power, but that's really not necessary. Plus what's left of the second term. We factor out x squared minus 4 squared and 2x, so all that's left is the 3 times x squared. 3x squared. Okay, let's keep going here. X squared minus 4 squared. Well, it was just x squared minus 4. That's different to perfect squares. I would factor in x minus 2x plus 2. And it still does. But since we have 2 of these, and it's squared, when it factors, we have 2x squared minus 2's and 2x squared plus 2's. And then over here, we can combine some like x squared plus 3x squared. It's 4x squared, and then minus 4. Then you can factor out a GCF of 4. That would be easiest if we just multiply it by the by the 2x out in front to give you 8x. Sorry about that. There we go. So factoring out the 4 here times 2x gives you 8x. It's minus 2 squared times x plus 2 squared. And then we're left with x squared minus 1. But I can factor a little bit further. These terms stay the same. But then x squared minus 1, another difference for the squares. Factoring x minus 1, x plus 1. Okay, so this time we've got 5 different things that are going to go on our number line. Those critical numbers. Got 0, 2, -2, 1, and -1 are the zeros that make the second root of 0. So in order, -2, 1, 0, and 2. And we get f double prime of x. All these, again, there's no denominator, so all these just make the second root of 0. And let's test, but before we test, let's see if we can find these shortcuts. Notice we've got squared on a couple of these, so we don't have to worry about these ever being negative. And other than 2 and -2 making them 0, they're always going to be positive. So we really only have to test into the 8x, the x minus 1, and x plus 1. So, for instance, we test -3 times 8 is negative. -3 minus 1, negative. -3 plus 1, negative. 3 negatives multiplied together is negative. Test -1.5 times 8 is negative. -1.5 minus 1, negative. -1.5 plus 1, still negative. 3 negatives still multiplied together, still negative. Here you can test -1/2 between -1 and 0. So -1/2 times 8 is still negative. -1/2 minus 1, negative. And -1/2 plus 1 is finally something changes to positive. 2 negatives times a positive is positive. 1/2 times 8 is positive. 1/2 minus 1 is negative. 1/2 plus 1 is positive. 2 positive times a negative is negative. 1.5 times 8 is positive. 1.5 minus 1 is positive. 1.5 plus 1 is positive. 3 positive multiplied together is positive. And 3 makes them all positive as well. So this shows us for f of x, it's concave down, concave down, concave up, concave down, concave up, and concave up. So let's take a look and see where our points of inflection are. Not at -2, it stays concave down, but at -1, the concavity changes. At 0, the concavity changes. At 1, the concavity changes. But at 2, it stays concave up. So in this case, out of our 5 possible points of inflection, only 3 of them turned out to be inflection points. So we can say f as inflection points, same thing as the points of inflection. X equals -1, x equals 0, and x equals 1. And we can say, write down the intervals in which f is concave up and concave down. F is concave up on -1 to 0, union 1. You could stop at 2, but since it's 0, you can go all the way to infinity. F is concave down on -infinity. And you could stop at -2, but since it's 0, you don't have to. You can go all the way to -1. Union also from 0 to 1. Let's take a look at one more example. This time, in some ways, it's the easiest of all because we're given, consider a differential function f with a given second derivative. So we already have the second derivative. And again, we're asked for the same thing. Find the x coordinates for the inflection points and state the intervals on which f is concave up and concave down. But since we have the second derivative already, we don't need to take the derivative at all. It already is a second derivative. And it's almost in most simplified form. We've got -2x cubed, we've got 2x minus 3 to the fourth. The only thing that can be simplified a little further is this x squared minus 9 comes back to x minus 3, x plus 3. So one of those factors equaling 0, those would give us all our critical numbers. Let's just put them on the number line. So we've got 0 from right here. We set that equals 0, you add 3 divided by 3 halves. 3, and negative 3. So the first one we get is negative 3. Oops. Then 0, then 3/2, and then positive 3. And again, all these make the second derivative f double prime of x equal to 0. We just have to test between them. See if we can find any shortcuts on this one. Notice we've got x cubed, that could be positive, negative, it's an odd exponent. But if we have 2x minus 3 to the fourth, that's even. So that's going to always be positive except for 3/2. So we only have to test in these three factors. So let's say we start with negative 4. And the cubed is negative, but times negative 2 makes it positive. Negative 4 minus 3, negative. Negative 4 plus 3, negative. Positive times 2 negatives is positive. Between negative 3 and 0, negative 1. Cubed is negative, times negative 2 is positive. Negative 1 minus 3 is negative. Negative 1 plus 3 is positive. So 2 positive times negative is negative. We test positive 1 here, between 0 and 1.5. 1 cubed is positive, times negative 2 is negative. 1 minus 3 negative. 1 plus 3 positive. 2 negatives times a positive is positive. 2 cubed is positive, times negative 2 is negative. 2 minus 3 negative. 2 plus 3 positive. 2 negative times a positive, still positive. And 4 cubed is positive, times negative 2 is negative. 4 minus 3 positive. 4 plus 3 positive. 1 negative times 2 positive. So this shows us f of x concave up, concave down, concave up, still concave up, and then concave down. And our possible points of inflection, there's 4 of them. At negative 3, it is a point of inflection because the graph switches concavity. So is 0, the graph switches concavity. 3/2 is not because it stays concave up, and 3 is also a point of inflection, it switches from concave up to concave down. So we can say f has inflection points at x equals negative 3 equals 0 and x equals 3. F is concave up on negative infinity, negative 3, union, and 0 to 3. And you don't have to stop at 3/2 since the second derivative is 0 there, although you could. And f is concave down on negative 3 to 0 and 3 to infinity. And that concludes the notes for AP Calculus on the topic of concavity and points of inflection.